And so we're going to kind of take a look a little bit more at what the cell really looks like. Not cell, the atom really looks like. I'm in biochem already. And so at this moment in time, the structure of the cell, what shape is it that you know? If it's in three-dimensional space, it takes up the shape of a sphere. Little tiny balls, okay? Inside there, is it solid completely? No, where's the solid part? In the nucleus. Very tiny. That's where all the mass is. And then we said the electrons are buzzing around, taking up the volume, okay? But what we haven't done is describe for you in very much detail where those electrons are. And if I give you a little preview, radioactivity is when the nucleus falls apart, either a piece falls out or energy falls out. So that's a nuclear process or radioactivity. When we actually look at chemistry, chemistry is only involving the movement of electrons. And so in a chemical reaction, electrons are moved around, or that's where the chemistry actually happens. Chemistry doesn't happen in the nucleus. That's a physics type of concept. And so the electrons are very important to chemists, and we think they're just buzzing around right now without kind of a defined shape or area. But further experiments are going to lead us down the road to describe that the electrons within the atoms are actually very defined around that center. They don't just buzz everywhere they want to be. They are in very specific and defined areas. And so we're going to look at some of the reasons why that we came to this conclusion and some of the principles that we needed to know so that we could get to that conclusion. And so that's what we're going to look at: development of the modern atomic model and the electron structure of the modern atom. All right. Now, it all has to do with energy. And energy is characterized in two main ways, one lesser way. Okay? An energy wave is described in terms of frequency and wavelength. And so if you are hit with any kind of energy, we can describe that energy as having a specific wavelength, and this wavelength will be in meters, and a specific, looks like a V, but it is the Greek letter nu, a specific frequency based in what we will call hertz or 1/second. Okay? Wavelength is easy to understand. How big is the wave? And when we measure the wave, we measure it from peak to peak or trough to trough. It is actually a wavelength. It could be in meters. It could be in larger than meters or smaller than meters. Okay? The frequency is per second. How many times does that wave hit you in 1 second? So is it really, really fast, or is it really, really slow? Do you get hit 3 times a second or 1,000,000 times a second? And between the frequency and the wavelength, there is a relationship. If you change one of the frequency, then the wavelength automatically changes, and they're linked between the two. There is one more lesser, and that's amplitude. Amplitude is the amount. So an energy could be, let's say, the light coming out of a flashlight. Okay? The light coming out of a flashlight has a certain color. The color represents a wavelength and a frequency. Now, that flashlight can be very dull, or it can be very bright. If it is very bright, it has a high amplitude. If it's very dim, it has a low amplitude. The amplitude doesn't change what kind of light it is or what kind of energy it is, just how much is there. But frequency, if you change that, will change the wavelength, and it changes the color if it's invisible, or it changes what that wavelength is, changes what that energy is. So we're going to be looking at wavelength and frequency when we're describing, when we're describing the energy. Okay, and so let me talk about what kind of energies there are. And so when we talk about energy, we're going to talk about electromagnetic radiation. Okay, radiation, we've already learned, were three parts that came from the nucleus: alpha particle, beta particle. Okay, we're not talking about that one. The other one was gamma rays. Okay, gamma ray is an energy. That is actually part of this electromagnetic spectrum. So there's going to be electricity involved, and there's going to be magnetism involved with these energy waves.
Waves are periodic changes in electric and magnetic fields which propagate through the space. The electric and magnetic field vectors E and B are at right angles to each other and at right angles to the direction of travel. Gamma rays, X-rays, ultraviolet radiations, visible light, infrared radiations, microwaves and radio waves are electromagnetic waves. Did you know that every time you get sunburn or feel the sun's rays, tune in your radio set, get X-ray done, or make popcorn in the microwave, you are using a different form of electromagnetic energy? The alternate distribution of electromagnetic waves according to their frequencies or wavelengths in the form of separate groups having widely differing properties is called electromagnetic spectrum. Displayed here is the electromagnetic spectrum. Click on the arrows to view the components of the electromagnetic spectrum.
So on one end, there's gamma rays, followed by X-rays, followed by UV light, followed by visible light, followed by infrared, followed by microwaves, and then all the way at the end, radio waves. And so all of these energies, from gamma rays all the way to radio frequencies, are exactly the same in terms of they are energies. But what we can perceive or how much energy each one carries is different based upon the wavelength and the frequency that it has. And so we said gamma rays were like X-rays, but they're worse in terms of energy because they're further to one side of this spectrum. Okay? And radio waves, we get hit with radio waves all the time. Does anybody even listen to the radio anymore? Okay, what radio station might you listen to in this area?
Spirit FM or The Journey.
Yeah, what is their numbers? Do you know?
It's like
105.3. 105.3. J103.1. All right, and there are, or if you're NPR, 88.1 on the FM dial. If you're really old and boring, you listen to NPR. And so there are radio frequencies flying around. All right. Are the radio frequencies only there when you turn on the radio? No. Right this moment, you are getting hit by radio waves. Is it hurting you? No. Now, it only hurts me when I tune into a country station and I hear what's going on. All right. But it's not actually hurting me. Now, what if you stepped inside a microwave and you turned it on? That would not be good, okay? Or what if you're continuously hit by X-rays? Not so good. And so some energies that you get hit by don't really hurt you too much, but other waves can. It's because each one carries a different energy. We'll be able to calculate how much energy each one does in just a little bit. But here's the deal. They're on this spectrum. There is a numerical value that starts at one end and goes to the other end, and there is an energy that is represented at every wavelength known that we know of. And they just get into a category when they start behaving a little bit differently with the real world. And so we can get hit by radio waves all we want. Doesn't really affect us as, let's say, gamma rays would hit us. The only one that we actually really realize that the energies are flowing around is the light waves, because we have a detector that we carry around with us all the time that actually detects light, and that's our eyeballs. We respond to those in a way that we can perceive. We see those wavelengths. We respond to UV light. As you saw, if you go out and you lay on the beach, what can happen? You can get a tan, right? Or you can get burnt. For some people, it takes like 2 seconds, and they go from tan to burnt, right? But if some people can tan, you know what you're doing to yourself? You're basically cooking yourself real slowly. And you know you get brown because you're cooking yourself, okay? Just like it would be. Now, all of these energies represent something. Now, we understand what radio waves are. We understand what a microwave is. Infrared, that's something that's a term that we don't use too often. IR glasses, infrared, is also night vision. When we look through night vision glasses, what are we actually looking at? Yeah, the signatures from infrared waves. If we put that into normal speak, not scientific speak. If I had to describe that to someone who is not a scientist, what is infrared energy? Heat. Okay? The energy of heat is a wave, and it is in the infrared region. Visible, we know. UV light, we can't see, okay? But it can cause damage. Once we get past visible, we start getting into energies that are damaging. X-rays go through you, through the soft tissue, but not your hard tissue, and that's why we can use them for X-rays. And gamma rays will just go right through you, and if by chance it hits you, it can cause major damage very quickly. But they're all a spectrum. Now, when you turn on a light bulb, okay, you get what color light normally? It's kind of what? What would you say? Yeah, white, sometimes yellow, from a light bulb. And now we can buy fluorescent, not fluorescent, but LED bulbs, and you actually select what color. Have you seen different LEDs? One are like a little bit more yellow, one's a little bit more blue. We actually have the ability to select what light we like. Some they call daylight, some they call soft light, and some people like one or the other. But we can now go into the store and select what kind of color we want. The common wavelengths, when we look at these, X-rays are in what we call angstrom, which is a different unit. It's 1 times 10 to the minus 10. The visible and ultraviolet are in the nanometer range. Infrared is in micrometers and millimeters. Microwaves are in centimeters, and radio and TV are in meter range. So the scale, they get larger in terms of their wavelengths. And so here is how we relate the two. And what we get is this right here. This is the biggie. Okay? All energy goes at the same speed. Okay? The speed is limited by a constant number, and it is the speed of light, which is 3.00 e to the 8th meters every second. Okay? So that's a big conversion factor that you need to know. Now check this out. Speed has a value of, or a unit of meters per second. The frequency has a unit of per second times the wavelength has a unit of meters. And so when you multiply the frequency and the wavelength, you get a speed, meters per second. And every time you do that calculation, it always has to equal c, the constant light of speed. So if one goes up, the other one has to go down when you do these kinds of calculations. And so if you use a laser to do eye surgery, now that sounds great. All right, you think of a laser, right? And it's very intense, can have a lot of energy, and you're going to hit it in your eye. All right, only the doctor should do it. It has a wavelength of 640 nanometers. What is its frequency? All right, well, we've got an equation, right? We've got C equals the wavelength times the frequency. What are we given? Are we given a wavelength or a frequency? A wavelength. Okay? And so what we have to do is convert that. Oh, I hit the button. And if we do that, we can find the frequency is, divide both sides by the wavelength, C equals, or C divided by lambda. Now here's the problem. I'm giving a wonderful wavelength. I'm given a value number. Is it all going to work out for good? Can I just put on the top 3 times 10 to the, or 3 times 10 to the 8 meters per second and divide it by 640? Why can't I do it? I can tell, I'll say you can do it, but why would that be wrong? It's nanometers, and your constant number has meters in it. So before you do anything, you must make sure that you convert the nanometers into meters so that the meters cancel out and you're left with a frequency which is, and remember, 1 over s is equal to s to the minus 1, which is equal to, we call it hertz. All of those units are exactly the same, and you can interconvert or just put them in the equation at any place in time. And so, using this, the only thing that you have to watch out for is converting to the proper unit. So when you actually use C, all of your wavelengths have to be in meters, and all of your frequencies have to be in hertz. All right. Now, out of this idea, there were 2 competing ideas about energy. And one is heat, which is the infrared range, and one is light, which is in the visible range, or even in the UV range. And what people were trying to identify, Planck and Einstein were 2 of the main players in this, was to actually calculate the energy of each piece of, or the actual, evaluate exactly the amount of energy that can be released or absorbed by atoms. And so there was the thought, just like atoms were the smallest tiny piece of matter, there was an idea that there was a smallest value of energy that could be transferred from any one atom to the next. Now, if you got more energy, you got 2 of them, or 3 of them, or 4 of them, but there was a smallest unit, and so there was a race to decide what that was. And 2 values came up, or 2 names came up for the values. If you're talking about heat, originally, we talked about quanta of energy. And if you talked about light, they termed that one a photon of energy. But regardless of if you're talking about a quanta of energy, a quantifiable small piece, or a photon, one single light piece, they came up to the same value. The value was defined by this equation. The energy is equal to some constant number times the frequency. And this constant number is this, Planck's constant. Now, conversion factor. Need to memorize this one. 6.626 e to the minus 34, and the unit is joules times a second. Now, joule. Joule is an energy source. Okay. Now, you don't use joule too often. If you think about a value for energy, especially with food, what is the energy value of food? What do you look up on the label? Calories. All right. And so there is a representation that is between joule and calories. If you actually look in Europe or outside the U.S. and you look up calorie count, you won't find it. You'll actually find joules as the measure, and so because it is the metric value. So that's the amount of energy. Now, look at that number. Tell me something about that number.
Extremely small.
Yeah, extremely small. This is 0 point, and then 33 zeros before you even have a number. 6. 626. Okay? Energies can be transferred in little tiny packets. Okay? But we transfer lots of them. And so, energy and frequency are combined together. Now, wait a minute. Check this out. You have two equations. Energy is equal to what? H, which is Planck's constant, and nu. And how do we relate the frequency and the wavelength? What are they equal to? Frequency and wavelength is equal to something? C, which is what? The speed of light. And what do we have to do to the frequency and the wavelength to get the speed of light? We do what? Multiply them. Uh-oh, do you see something? Between those two equations. They both have what looks like a V, it's a nu. And so if you solve one, you can plug it into the other. And because they have a similar value, if I solve for this, I get C over this equal to nu. And then if I do this, I get E over H equal to nu. And if they're both equal to something, then what can I make them? Equal to what? Each other. So, that is the worst H I've ever seen. So, these two equations can be combined because they have a variable that is common between them. Okay? And so, we're going to use these equations to calculate things. All right, so let's use these equations to calculate things. All right. Work with your partners around. Check your work. Hopefully your work matches. If you work with 4 partners and get 4 different answers, then debate amongst yourselves. All right. So I gave you some stuff at the bottom. Oh, one good thing on the exam, bring pencil. Chemistry is so much better in pencil. Also, know your ID number because you're going to be filling out a bubble sheet that you have to put your ID number in, so know that. That would be good. Your ID number is not on your ID card. Okay, let's look at that first one, just a few steps of it. Okay, someone tutor me. What equation do I use? You start with the speed of light is equal to the wavelength times the frequency. All right. Do I know any one of these variables? Or any one of these? You know two of them, right? Why do you know this one? It's given, but it's also a constant. It never changes. What else do you know?
The frequency.
You know the frequency. How in the world do you know the frequency? Because it's in the problem, right? So that means I have to mathematically convert it so that the frequency or the wavelength that I want is C over nu. Okay. Now when I do the C, which is what number? What is that number? 3.00 e to the 8th meter over a second, and I divide it by what I'm given, 4.80 e to the 12th And I'm going to put it like this, 1 over second. Okay. Mathematically, the seconds on the bottom cancel. Okay. And if I finish the problem now, what value do I have? You have it in meters. I'm done, right? No. Why am I not done? The answer needs to be in centimeters. Uh-oh. Can you convert meters to centimeters? I hope so by this point in time. And then I would do this. Stop. I totally lost all of it. All right. The last part I would have done was this. Meter, centimeter. That's a very light. Meter and centimeter. I would have put 1 centimeter over 1 e to the minus 2 meters to finish up that problem. All right. Anybody brave enough to get a number on that one? 6.25 e to the negative what? Anybody else get negative 3? Centimeters? Okay, that is the answer for that one. All right. What about this one? What equation do I use for this one? I have to use, I want energy. The only thing I know about energy is E is equal to H nu. All right. So I know E, or no, sorry, I don't know E. I want E, right? Because that's what it says, energy in joules. I have one of them, Planck's constant, because that's a constant. And what else do I have? I have a frequency, right? And in this frequency, it's kind of weird. It is 1140 kilohertz. All right. What in the world is that? Well, AM dial is kilohertz. The FM dial is megahertz, actually. And so it is a frequency, but it's got one of those prefixes in front of it. And so what I need to do is I need to take this value, which is a nu, and multiply it by Planck's constant. And so if I start off with that number, I get kilohertz, okay, which is kilo 1 over s, hertz. That's a problem, because I don't want kilohertz. I want just hertz. And so if I have kilohertz just into hertz, then I know that one of these is what? 1 e to the third hertz. And so now, at this moment in time, I have frequency in terms of hertz, which is that unit there. And then I multiply it by Planck's constant, which is 6.626 e to the minus 34 joule second. All right, what in the world? A second on the bottom, a second on the top. The seconds cancel out. I'm now left with joules. Anybody get a number on that one? $7.55 e to the negative 28 joules. Feel good? Anybody else get that number? Okay. All right, last one. A little bit different, isn't it? Okay. What am I given? You're given a wavelength. The wavelength is that equation. And what do you want? An energy. That's that equation. Okay? So, if this equation is C equals wavelength times nu, then if I have wavelength, I can find out the wavelength, the nu is equal to C over lambda. And if I have energy, it's H nu. Well, this nu is that nu. So what I'm going to do is, instead of putting nu here, I'm going to put the value of this. So I'm going to put the energy is equal to Planck's constant, and I've redefined nu as this thing. The speed of light divided by the wavelength. Now, is there any problem with this? Well, mathematically, if everything was in meters and seconds, meters and per second, we'd be fine. Is it given in? No. The last thing you have to do is convert. Okay? You would have to convert what's given for centimeters into your unit of meters. So I would solve this by doing this. Take H. A joule and a second. And I would multiply it by the speed of light. And that is meters over a second. And I would divide it by the wavelength I have for centimeters. But the problem is those centimeters have to be converted into meters. And 1 centimeter is 1 e to the minus 2 meters. And if I start canceling things out, second on the bottom, second on the top, meter on the top, meter on the top, centimeter on the top, centimeter on the bottom, I have gotten rid of all of my units except for joules, which I want because that's a value of energy. Does anybody have a number for me? 4.9695. Oh, e to the negative 24. That can't be my answer. What is really my answer? Based on sig figs? What is it? Nope. 5. E to the minus 24 joules. Why 5? Started with 1. Have to end with 1. Because these are all multiplications and divisions. Okay? So, I could give you wavelength, make you basically find frequency. I can give you frequency, make you find wavelength. I can give you frequency, make you find an energy. I can give you a wavelength and make you find the energy. I can give you energy and a wavelength and make you find frequency. So I can give you 2 of the things and make you find the other. Or I can combine the 2, and you'll have lots of practice to do that in a little bit with your homework. Okay. All right. All right. The last idea that we're going to talk about is the photoelectric effect, and I thought I had gotten this. So let's go to
electrode in an evacuated tube, as shown here, is
okay. Go back.
when an electrode in an evacuated tube, as shown here, is coated with an active metal. Electrons may be emitted from the metal when it is irradiated by light. This effect is called the photoelectric effect. Einstein explained the photoelectric effect by using Planck's concept of light as a stream of photons. When light of long wavelength impinges on the electrode, no electrons are emitted. Einstein proposed that this is so because the individual photons do not have sufficient energy to dislodge an electron from the attractive forces of the metal. Even when the light intensity is increased, there is no emission of electrons and no current flows. When light of shorter wavelength strikes the surface, electrons are emitted and are drawn to the anode. Thus, a current is seen to flow. Einstein proposed that the photons of shorter wavelength light impart sufficient energy to the electrons to enable them to escape from the metal. The kinetic energy of the electrons is the excess of that which they require to escape from the metal. When the intensity of the shorter wavelength light is increased, more electrons are emitted, and the observed current increases. However, the excess energy which the electrons possess remains the same. A higher intensity of light increases the number of electrons emitted, so the current increases. However, because each photon still imparts the same energy to each electron, the kinetic energies of the electrons remain the same. When light of still shorter wavelength is employed, the electrons are emitted from the metal with higher kinetic energy. This is so because the higher energy photons have imparted more energy to the electrons, and more kinetic energy remains after they escape from the metal.
Okay, so the photoelectric effect.
The electron pairs that surround the central atom are most likely.
Stop. Okay, the photoelectric effect from Einstein. It was the evidence that light is a little bit different. Light itself has both an energy component, acts and behaves like an energy, but it also acts like a particle. If he shined light of a certain wavelength, and there was a minimum that had to be in terms of its wavelength, electrons would actually start coming off of the metal. It took shorter and shorter and shorter wavelengths. The shorter the wavelength, the more energy. Remember, radio is huge, doesn't hurt us, but when we get down to shorter and shorter and shorter, you get X-ray and gamma ray, that starts to hurt us because each photon has more light. More energy. And so the amount of electrons coming off certain metals is determined by a certain wavelength. It has to get to a certain wavelength before anything comes off. Once you hit that, the intensity will kick off more or less, but you must reach a certain level. That means you must reach a certain level of energy for the electrons in any one metal to start to kick off. And after all of these experiments, what he came up to and determined was that the energy of light was governed by an equation called E equals Planck's constant times nu. And so working at two different ways, working at heat and working at light, both of them came to the same conclusion. Planck did it first, so it's Planck's constant, not Einstein's constant. And that's why H is Planck's constant. Okay, and so we can calculate the energy by multiplying the constant times the frequency and come up with an energy value for any wavelength and any frequency given. And so we can calculate E. All right. Last concept. What am I looking at here? A prism.
So the prism can be used as a spectrograph. In other words, used to separate colors. The prism is the triangular object in the middle, made out of glass. From the bottom left, you see the incident beam of light, which is white light, and towards the top, it's partially reflected. But within the prism, the white light is refracted, and then when it hits the surface to the right of the prism, it's refracted and dispersed at the same time. And the result of this is the rainbow that we...
Okay, so the rainbow. White light in itself has the full spectrum or every color mixed in. And when all of those colors mix in, we get white. We can use a prism to show that every single color is represented there. Okay? And so we're going to use the prism and other light sources to see something very strange. Now, does